Close your eyes and listen. Beyond the hum of the modern world, beyond the noise of daily life, there exists a sound so ancient, so persistent, that it has outlived civilizations. It is the sound of water meeting shore, the rhythmic exhale of the ocean as it touches land, then withdraws, then returns again. Tonight, we stand on a beach shrouded in darkness. The moon hangs above us, a luminous companion in the velvet sky. The waves roll forward with deliberate patience, each one whispering secrets carried from distant depths. The tide is rising. Slowly, inevitably, the water climbs higher up the sand, erasing footprints, swallowing shells, reclaiming territory it left only hours before. This is not random. This is not chaos. This is the pulse of the planet, a heartbeat measured not in seconds, but in hours. Twice each day, the ocean inhales, drawing breath from some invisible source. Twice each day, it exhales, releasing that breath back into the vastness. But what makes the water move this way? What invisible architect orchestrates this eternal dance? The tide has mystified humanity for millennia. Ancient sailors watched it with reverence and fear, knowing their ships could be stranded if they mistimed its rhythm. Coastal communities built their entire existence around its predictability, harvesting shellfish when the water retreated, launching boats when it returned. The tide was reliable, yet mysterious. Present, yet unexplained. For thousands of years, we watched without truly understanding. We created myths to explain the rising and falling water. Some cultures believed a great beast swallowed the sea and spit it back out. Others imagined gods breathing beneath the waves, their divine respiration moving the oceans. But the truth, as we would eventually discover, is stranger and more beautiful than any myth. The truth involves forces that reach beyond our atmosphere, beyond our sky, into the depths of space itself. The ocean is moved by gravity, not just the gravity of Earth, but the gravity of distant worlds, pulling across the void with invisible hands. Tonight, we will follow those invisible threads. We will trace the connection between sea and sky, between tide and cosmos. We will discover how the moon commands the waters, how the sun adds its voice to the song, and how planets millions of miles away might whisper their influence into every wave that crashes against the shore. The ocean is not alone. It has never been alone. It is held in the embrace of the solar system, responding to celestial rhythms that were set in motion long before the first fish swam in the sea. Breathe deeply. Let the sound of the waves wash over you, and prepare to journey from the shore to the stars, discovering what truly moves the water that covers most of our world. There is a companion that has walked with Earth since the beginning, a silent guardian that has witnessed every moment of our planet's history. It was there when the first rains fell and filled the ocean basins. It was there when the first cells divided in the primordial sea. It was there when the first creatures crawled onto land. And it will be there long after humanity has faded into memory. The moon, only 238,855 miles away, close in cosmic terms. Close enough that you can see its craters with the naked eye. Close enough that its gravity reaches down through space and touches everything on Earth, including you. Including the vast oceans that cover 71% of our planet's surface. Gravity is the universe's way of making connections. Every object with mass pulls on every other object with mass. Right now, you are pulling on the moon, just a tiny, imperceptible amount. And the moon is pulling on you with much greater force. But you don't feel it because you're standing on Earth, and Earth's gravity is so much stronger that it overwhelms all other influences. But the ocean is different. The ocean is fluid. The ocean can move. Imagine the Earth as a ball wrapped in water. As the moon orbits around us, its gravity tugs on that water, pulling it slightly toward itself. This creates a bulge, a subtle swelling of the ocean on the side of Earth facing the moon. The water rises, reaching upward as if trying to touch its celestial companion. But here's where it becomes truly fascinating. There's another bulge on the opposite side of Earth, the side facing away from the moon. Why? Because the moon isn't just pulling on the ocean. It's pulling on the entire planet. The solid Earth is pulled slightly more than the water on the far side, creating a second bulge. Two bulges on opposite sides of the world, both created by the moon's gravitational embrace that Earth rotates. Through these bulges, one full rotation every 24 hours, any given point. On the surface experiences 2 high tides and 2 low tides each day. The water rises. The water falls. The water rises again. This is the moon's gift to Earth, a predictable rhythm, a reliable cycle, a cosmic metronome that has been ticking since the moon first formed. Scientists believe the moon was born from violence. About 4.5 billion years ago, a Mars-sized object collided with the young Earth. The impact was so catastrophic that it vaporized rock and sent debris spiraling into orbit. That debris eventually coalesced into the moon. So in a very real sense, the moon is made of Earth. It is a child of this planet, forever bound by gravity, forever dancing in the sky. And since that ancient beginning, the moon has been shaping the tides, shaping the coastlines, shaping life itself. Consider the horseshoe crab, a living fossil that has existed for 450 million years. These ancient creatures time their spawning to the highest tides of spring, when the moon is full and its gravitational pull is strongest. They crawl onto beaches by the thousands, lay their eggs in the wet sand just beyond the tide line, and retreat back into the sea. 2 weeks later, when the next high tide arrives, the eggs hatch, and the larvae are swept into the ocean. This is a ritual older than dinosaurs, choreographed by the moon. Or think of the mangrove forests that thrive in tidal zones, those liminal spaces between land and sea. Their roots are adapted to tolerate being submerged twice a day, then exposed to air. They couldn't exist without the tide. And those forests, in turn, provide nurseries for countless fish species, filter pollutants from coastal waters, and protect shorelines from erosion. The moon creates the tide. The tide creates the habitat. The habitat sustains life. Even human civilization has been profoundly shaped by lunar rhythms. Ancient calendars were based on the moon's phases. Religious festivals were timed to full moons. Farmers planted and harvested according to lunar cycles, believing the moon influenced the moisture in soil. Whether or not those beliefs were scientifically accurate, they reflect a deep human intuition that we are connected to the moon, that its presence matters, and that intuition is correct. The moon doesn't just create tides in the ocean. It creates tides in the atmosphere, subtle pressure variations that can influence weather patterns. It creates tides in the solid Earth itself. The rock beneath your feet rises and falls by several inches each day, flexing under the moon's pull. You don't notice it because you're moving with it, riding the wave. Some researchers have even found correlations between the lunar cycle and human biology. Sleep patterns change for some people around the full moon. Hospital emergency rooms report slight increases in certain types of incidents. The evidence is debated and often contradictory, but it raises an intriguing possibility that we carry the memory of the tide within us. An echo of our evolutionary origins in the SEA.as you drift now. Imagine the moon overhead, pulling gently on the waters of the world. Imagine the tides responding, rising and falling in slow synchrony. Imagine yourself connected to that rhythm, part of an ancient pattern that links the smallest tide pool to the vastest ocean, the shoreline to the sky. But the moon is not the only voice in this celestial choir. There is another conductor, another force, blazing with light and warmth. The sun is about to join the performance. Dawn arrives with soft color, first deep blue, then violet, then a hint of gold spreading across the horizon. The stars fade. The moon becomes translucent, a ghost of its nighttime self. And slowly, inevitably, the sun rises, spilling warmth and light across the water. The sun is 93 million miles away. It is 400 times farther from Earth than the moon, but it is also 27 million times more massive. These two facts almost balance out. Almost, but not quite. The result is that the sun does exert a gravitational pull on Earth's oceans, but it's only about 46% as strong as the moon's. Still, 46% is significant. The sun is a partner in the tidal dance, adding its rhythm to the moon's, creating patterns of reinforcement and interference. When the sun, moon, and Earth align, which happens during new moons and full moons, their gravitational forces combine. The sun's pull and the moon's pull work together, creating what we call spring tides. These are the highest high tides and the lowest low tides of the month. The ocean swells dramatically, reaching farther up the beach. exposing more seafloor when it retreats. Coastal areas can experience flooding during spring tides, especially when combined with storms. But when the moon is at a right angle to the sun during the first and third quarter moons, their gravitational forces partially cancel each other out. The sun pulls in one direction while the moon pulls in another. The result is neap tides, when the difference between high and low water is minimal. The ocean's breath becomes shallower, gentler, more subdued. This creates a monthly cycle layered over the daily cycle. Every day, 2 high tides and 2 low tides. But every 2 weeks, those tides reach extreme ranges during spring tides, then moderate during neap tides. It's a rhythm within a rhythm, a pattern that coastal dwellers have observed and depended upon for thousands of years. But the sun's influence on the ocean extends far beyond gravity. The sun is the ultimate source of nearly all energy on Earth. Every ray of sunlight that strikes the ocean's surface carries warmth, and that warmth sets the entire planetary system in motion. Water evaporates from the ocean, rising as invisible vapor into the atmosphere. That vapor forms clouds, travels on wind currents, and eventually falls as rain or snow, feeding rivers that flow back to the sea. This is the water cycle, and it's powered entirely by solar energy. The sun lifts water from the ocean, carries it across continents, and returns it in an endless circulation. The sun also drives the great ocean currents, those vast rivers of water that flow through the sea, carrying heat from the equator toward the poles and bringing cold water back toward the tropics. The Gulf Stream, for instance, moves warm water from the Caribbean up the eastern coast of North America and across the Atlantic to Europe, making the climate there much milder than it would otherwise be. Without the Gulf Stream, London would have the same winter temperatures as Labrador. These currents are driven by temperature differences created by the sun. Warm water is less dense than cold water, so it rises and flows toward the poles while cold water sinks and flows toward the equator. This creates a global circulation pattern called the thermohaline circulation, sometimes poetically called the ocean conveyor belt. It takes about 1,000 years for water to complete one full journey through this system. The sun also fuels photosynthesis in the ocean. Phytoplankton, microscopic plants drifting in the sunlit surface waters, absorb sunlight and carbon dioxide, producing oxygen and organic matter. These tiny organisms form the base of the ocean food web. They feed zooplankton, which feed small fish, which feed larger fish, which feed whales and sharks and seabirds. Every bite of food taken by every marine creature can be traced back to sunlight captured by phytoplankton. In fact, phytoplankton produce about 50% of the oxygen in Earth's atmosphere. Every other breath you take comes from the ocean, created by microscopic organisms powered by the sun. The ocean and the sun are not separate entities. They are partners in sustaining life. And just as the sun warms the ocean moderates the sun's effects. Water has an enormous capacity to absorb and store heat. The ocean acts as Earth's thermostat, preventing temperatures from swinging to extremes. Coastal areas have milder climates than inland regions because the nearby ocean absorbs heat in summer and releases it in winter. So when we speak of the sun affecting the tides, we're only telling part of the story. The sun doesn't just pull on the water. It energizes it, circulates it, evaporates it, and uses it to regulate the planet's climate and support its life. As morning light spreads across the water. Imagine the sun and moon working in concert. Sometimes their forces align, creating powerful spring tides. Sometimes they work at cross purposes, creating gentle neap tides. But always, they are present. Always, they are pulling. Always, the ocean responds to their celestial choreography. Yet the solar system contains more than just the sun and moon. There are other worlds out there, massive gas giants and distant ice planets, all orbiting the same star, all connected by the same fundamental force. Could they, too, have a role to play in the movement of Earth's oceans? Look up on a clear night, away from city lights, and you might see a bright, steady point of light that doesn't twinkle like the stars. That's likely Jupiter, the king of planets, the largest world in our solar system. It's so massive that more than 1,300 Earths could fit inside it. Its gravity is powerful enough to fling comets out of the solar system or capture them into orbit. Jupiter is 365 million miles away at its closest approach to Earth. That's 1,500 times farther than the Moon. And yet, despite that enormous distance, Jupiter's gravity does reach across the void and touch our planet. The pull is extraordinarily faint, about 100,000 times weaker than the Moon's tidal force. It's far too subtle to create measurable tides in our oceans. You couldn't detect Jupiter's influence by watching the waves or measuring water levels. The effect is simply too small, but that doesn't mean Jupiter has no influence at all, because Jupiter doesn't just pull on the ocean, it pulls on the Earth itself. And over long periods of time, thousands and millions of years, those tiny, persistent tugs accumulate into something measurable, something profound. The Earth's orbit around the Sun is not a perfect circle. It's an ellipse, slightly elongated, with the Sun at one focus. The shape of that ellipse changes over time, becoming more circular for a while, then more elongated, then more circular again. This cycle takes about 100,000 years, and it's caused primarily by the gravitational influence of Jupiter and, to a lesser extent, Saturn. Why does this matter for Earth's oceans? Because the shape of Earth's orbit affects how much sunlight the planet receives. When the orbit is more elliptical, there's a greater difference between the closest and farthest points from the Sun. When it's more circular, the distance remains more constant throughout the year. These variations in solar energy input contribute to long-term climate cycles. They're part of what are called the Milankovitch cycles, named after Serbian scientist Milutin Milankovic, who first calculated them in the 1920s. These cycles help explain the timing of ice ages and warmer interglacial periods that have occurred over the past million years during ice ages. Enormous amounts of water are locked up in glaciers and ice sheets. Sea levels drop by hundreds of feet, exposing land bridges and reshaping coastlines. Ocean currents change their paths. Marine ecosystems adapt or migrate. And all of this is influenced, in part, by the gravitational effects of distant Jupiter and Saturn, slowly modulating Earth's orbit. Saturn, the ringed beauty of the solar system, adds its own voice to this cosmic orchestra. Though smaller than Jupiter, it's still 95 times more massive than Earth. Its orbital period is about 29 years. And when Saturn and Jupiter align on the same side of the Sun, which happens approximately every 20 years, their combined gravitational influence on Earth's orbit is slightly stronger. Some scientists have proposed that these planetary alignments might even affect the Sun itself. The Sun has tides, too, not water tides, but plasma tides, movements in the superheated gas that makes up its surface and interior. When the giant planets align, their combined gravity might subtly influence the Sun's rotation or its magnetic field. And the Sun's magnetic field, in turn, affects solar activity, sunspots, solar flares, and the solar wind. Changes in solar activity can affect Earth's climate, including ocean temperatures. More solar activity means more energy reaching Earth. Less activity means slightly less energy. These variations are small, but they can have measurable effects, especially when they persist over long periods. This creates a fascinating chain of connections. Jupiter and Saturn's gravity affects Earth's orbit, which affects climate. They might also affect the Sun's activity, which affects the amount of energy reaching Earth, which affects ocean temperatures and currents. Everything is connected. Every force, no matter how distant, matters. Even the smaller, more distant planets contribute to the pattern. Uranus and Neptune, the ice giants of the outer solar system, have their own subtle gravitational influences. Mars and Venus, our planetary neighbors, tug on Earth as they pass by in their orbits. The effects are minuscule individually, but they all add up, creating small variations in Earth's motion through space. There's also the phenomenon of orbital resonance, when the orbital periods of two or more planets form simple numerical ratios. For example, Neptune orbits the Sun 3 times for every 2 orbits of Pluto. This 3:2 resonance means their gravitational interactions reinforce over time, creating stable patterns in their orbits. Similar resonances exist throughout the solar system, and some researchers have investigated whether resonances involving Earth might amplify certain planetary influences. The evidence is still being gathered, the theories still being tested, but the possibility remains intriguing. that the architecture of the solar system, with its precisely spaced orbits and resonant patterns, might create subtle but real effects on our planet and its oceans. As you rest here, drifting between waking and sleep, imagine the solar system as a vast orchestra. The moon plays the principal melody, clear and strong. The sun provides the harmony, powerful and sustaining. And the planets, Jupiter, Saturn, and all the others, add subtle grace notes, barely audible but essential to the complete composition. The ocean listens to this entire symphony. It responds not just to the loud, obvious forces, but to the quiet ones as well. It integrates them all, mixing them into the complex patterns of tides and currents that have shaped our world for billions of years. But the planets affect Earth in another way, too, by influencing not just its orbit, but its orientation in space. The very angle at which Earth tilts, and the way that tilt changes over time, is subject to celestial choreography. Picture a spinning top on a table. As it spins, it doesn't remain perfectly upright. Its axis traces a slow circle, a wobble that becomes more pronounced as the top loses energy. This motion is called precession. Earth does the same thing. Our planet spins on its axis once every 24 hours, creating day and night. But that axis doesn't point in a fixed direction. It wobbles, tracing a slow circle against the backdrop of stars. This wobble takes approximately 26,000 years to complete one full cycle. Right now, Earth's north rotational axis points roughly toward Polaris, the North Star. But 5,000 years ago, during the time when the Egyptian pyramids were built, the axis pointed toward a different star, Thuban, and in about 12,000 years, it will point toward Vega. Then, after another 14,000 years, it will point back toward Polaris again. What causes this cosmic wobble? The gravitational tugs of the moon and sun on Earth's equatorial bulge. Earth is not a perfect sphere. It's slightly wider at the equator due to its rotation. The moon and sun pull on that bulge, creating a torque that causes the axis to precess, like a gravitational hand gently nudging a spinning top. But there's more. Earth's axial tilt, currently about 23.5 degrees, is not constant either. It oscillates between about 22.1 and 24.5 degrees over a cycle of approximately 41,000 years. This is called obliquity variation, and it's caused primarily by the gravitational influence of the moon, with contributions from the planets, especially Jupiter and Saturn. Why does this matter for the oceans? Because the axial tilt determines the intensity of seasons. A greater tilt means more extreme seasons, hotter summers and colder winters. A smaller tilt means milder seasons. And seasonal variations affect ice formation at the poles, which in turn affects sea levels and ocean circulation. During periods of greater tilt, summers in the polar regions are warmer, causing more ice to melt. But winters are also colder, allowing more snow to accumulate. The balance between summer melting and winter accumulation determines whether ice sheets grow or shrink. And the size of the ice sheets determines how much water is locked up on land versus flowing in the oceans. When ice sheets grow, sea levels drop. Coastlines shift outward. Shallow seas become dry land. The continental shelf is exposed. Marine habitats migrate. Species adapt or go extinct. And when ice sheets melt, the reverse happens. Sea levels rise. Coastlines retreat inland. Low-lying areas flood. And new marine habitats are created. All of this unfolds over tens of thousands of years, driven by the slow, patient wobbling of Earth's axis and the subtle gravitational influences of the moon and planets. There's yet another cycle to consider, the precession of the perihelion. This is the slow rotation of Earth's entire elliptical orbit. Remember that Earth's orbit is not circular, it's an ellipse. And the point of closest approach to the sun, perihelion, slowly rotates, completing one full turnabout every 112,000 years. Currently, Earth reaches perihelion in early January, during the Northern Hemisphere's winter. This means northern winters are slightly warmer than they would otherwise be, and southern summers are slightly warmer. But thousands of years ago, perihelion occurred in July, making northern summers warmer and intensifying seasonal contrasts in the northern hemisphere. These shifts in the timing of perihelion, combined with changes in orbital eccentricity and axial tilt, create the Milankovitch cycles we mentioned earlier. These cycles explain the ice ages and interglacial periods of the past million years. They explain why glaciers advanced and retreated, why sea levels rose and fell, why coastlines transformed and ecosystems migrated, and all of these long, slow cycles, is influenced by the gravitational dance of the planets, particularly Jupiter and Saturn, whose massive presence sculpts not just their own orbits, but the orbits of all the other planets in the solar system. The ocean responds to all of this. As climate changes, ocean currents shift. As sea levels change, coastlines migrate. As ice melts or forms, salinity changes, which affects water density, which affects circulation patterns. The ocean is not passive. It's an active participant in the climate system, absorbing heat, releasing heat, transporting energy around the globe. And beneath all of this, beneath the daily tides and seasonal currents, beneath the slow march of ice ages, there is the quiet persistence of planetary influence. Jupiter tugging, Saturn pulling, the moon stabilizing, the sun warming, all of them working together across vast distances and timescales to shape the motion of water on a small blue planet orbiting an ordinary star. As you sink deeper into rest, imagine Earth wobbling slowly through space, its axis tracing lazy circles against the stars. Imagine the planets in their orbits, their gravity reaching across millions of miles, nudging Earth ever so gently, patient and persistent. Imagine time stretching out, not measured in days or years, but in millennia and epochs to eye in this vast temporal ocean. You are a single moment, a brief ripple, but you are part of the pattern, connected to forces that have been operating since the solar system formed. The same gravity that moves the oceans moves you. The same cycles that shape climate shape the world you inhabit. And there is something profound in that, a sense of belonging to something much larger than yourself, something ancient and ongoing, something that connects the smallest tide pool to the vastest galaxy. But we're not done yet. There's another way to think about the ocean, not just as water in motion, but as a mirror reflecting something cosmic. Stand at the edge of the water as twilight deepens. The sun has set, but the sky still holds light, deep blue fading to indigo, then to black. The first stars appear, faint at first, then brighter as the darkness deepens. And below, the ocean reflects them. Each point of light has a twin on the water's surface, shimmering and dancing with the waves. The boundary between sea and sky dissolves. You can't tell where one ends and the other begins. They are mirrors of each other, each containing the other. This is more than metaphor. The ocean and the cosmos are fundamentally connected, not just through gravity, but through pattern and rhythm. The same mathematical principles that describe planetary orbits also describe ocean waves. The same physics that governs the motion of stars governs the motion of currents. Consider waves. When wind blows across the ocean's surface, it transfers energy into the water. That energy propagates as waves, rhythmic disturbances that travel across vast distances. Each wave has a wavelength, the distance between successive crests, a frequency, how many waves pass a point per second, and an amplitude, the height from trough to crest. These same properties describe light waves, sound waves, radio waves. In fact, they describe all waves, whether they're ripples on a pond or gravitational waves rippling through space-time itself. The universe speaks in the language of waves, and the ocean is one of its most eloquent speakers. Waves can interfere with each other. When two waves meet, they combine according to the principle of superposition. If their crests align, they create a larger wave, constructive interference. If a crest meets a trough, they cancel out, destructive interference. This creates complex patterns on the ocean's surface, regions of calm and regions of chop, constantly shifting and changing. The same interference patterns appear in quantum mechanics, where particles behave like waves and can interfere with themselves. They appear in acoustics, where sound waves create zones of loudness and silence. They appear in optics, where light waves create patterns of brightness and darkness. The ocean is demonstrating fundamental truths about reality. By watching waves interact on the water's surface, we're seeing the same principles that govern the deepest levels of nature. Or consider the tide itself. We've talked about how the moon's gravity creates tidal bulges, but there's another way to understand it. As a resonance. The moon's gravity provides a periodic force, pushing and pulling on the ocean twice a day as Earth rotates. The ocean responds to this forcing, sloshing back and forth in its basins. But the ocean isn't uniform. It's divided by continents, shaped by coastlines, deepened and shallowed by underwater topography. Different ocean basins have different natural frequencies. They want to oscillate at different rates. Just like different sizes of organ pipes produce different notes. When the tidal forcing matches a basin's natural frequency, resonance occurs. The tide is amplified, sometimes dramatically. The Bay of Fundy in Canada experiences the highest tides in the world, up to 50 feet between high and low water, because the bay's natural oscillation period matches the tidal period almost perfectly. The forcing and the response are in sync, creating enormous amplification. This same resonance principle appears throughout physics. It explains why a bridge can collapse if soldiers march across it in step. The periodic forcing matches the bridge's natural frequency. It explains how radio receivers work. They're tuned to resonate at the frequency of the station you want to hear. It explains the orbits of Jupiter's moons, locked in gravitational resonances that keep them in precise ratios. The tide is the ocean resonating with the cosmos. And by studying tides, we're learning about resonance itself, a universal phenomenon that connects systems across scales. Yet there's something else, too. The ocean moves in gyres, vast, circular currents that dominate each major ocean basin. The North Atlantic Gyre, for instance, includes the Gulf Stream flowing north, the North Atlantic Current flowing east, the Canary Current flowing south, and the North Equatorial Current flowing west, all connecting in a giant clockwise circle. These gyres are driven by wind patterns, which are in turn driven by Earth's rotation and the distribution of solar heating. But their motion echoes the rotation of the planet itself. Earth spins, and that spin is imparted to the atmosphere, which is imparted to the ocean surface, creating these great rotating currents. The same rotation appears in hurricanes and cyclones, in the swirl of water down a drain. Though contrary to popular belief, the direction of that swirl is not determined by the hemisphere. It's too small a scale for the Coriolis effect to matter. It appears in galaxies, vast spirals of stars rotating around a central core. Rotation is everywhere in the universe, from the smallest eddies to the largest structures. The ocean teaches us to see these patterns. By watching the water, we learn to recognize rhythms that appear throughout nature. By understanding tides, we understand resonance. By studying waves, we understand interference. By observing currents, we understand rotation. The ocean is a laboratory where cosmic principles are made visible. It's a place where the abstract becomes concrete, where mathematical equations become tangible phenomena you can see and feel. As you drift now, imagine yourself dissolving into that water. Imagine your boundaries becoming fluid, your sense of separation fading. You are not separate from the ocean. You are not separate from the cosmos. You are a pattern within the pattern, a wave within the wave, a rhythm within the rhythm. The same atoms that make up your body were forged in stars. The same water that flows in your bloodstream once flowed in ancient seas. The same forces that move the tides move the blood through your veins. There is no separation. There is only connection. And in that connection, there is peace. In the intertidal zone, that narrow band of shore between the highest and lowest tides, life exists in constant transition. Twice a day, this region is submerged beneath water. Twice a day, it's exposed to air. Organisms that live here must be adapted to both worlds. Equally comfortable breathing dissolved oxygen in seawater or gasping air from the atmosphere. Barnacles cluster on rocks, their shells tightly closed when exposed, opening to feed when the tide returns. Sea anemones retract into gelatinous lumps at low tide, expanding into flowing tentacles when underwater. Mussels clamp shut, holding moisture inside, waiting patiently for the ocean's return. These creatures have evolved to live by the tide. Their biology is synchronized with the rhythm of the moon. Their life cycles time to the ebb and flow of water. They are, in a very literal sense, children of cosmic forces. Consider the Christmas Island red crab. Every year, millions of these crabs migrate from the forest to the coast to spawn. But they don't choose the date randomly. They time it precisely to the lunar cycle, arriving at the ocean during the last quarter moon. when high tides are lower and less likely to sweep their eggs away prematurely. The females release their eggs into the water at dawn, just as the tide begins to turn, ensuring the larvae are carried out to sea. This is not learned behavior. Generation after generation, the crabs follow the same schedule, guided by instincts shaped over millions of years. They are reading the moon, responding to its cycle, integrating cosmic rhythm into their biology, or consider the palolo worm of the South Pacific. Once a year, during a single narrow window in October or November, these worms rise from the coral reef at dawn, precisely 2 days before the last quarter moon. Their bodies break apart, releasing eggs and sperm into the water in a mass spawning event so predictable that Pacific Islanders have traditionally harvested them as food, gathering on the beach on exactly the right morning. How do the worms know when to spawn? The mechanism involves multiple cues: lunar phase, water temperature, perhaps even subtle changes in light intensity. But the precision is remarkable. The worms are responding to celestial mechanics, to the position of the moon, to forces reaching down from space. Humans, too, have lived by the tide. For most of human history, coastal communities depended on tidal patterns for their survival. They knew which phases of the moon brought the highest tides, when the best fishing could be had, when shellfish beds would be exposed and accessible. Many ancient cultures created complex calendars based on lunar cycles. The Hebrew calendar, the Islamic calendar, the Chinese calendar, all are lunisolar or purely lunar, dividing time by the phases of the moon. These calendars served religious purposes, yes, but they were also practical tools for timing agriculture, predicting tides, organizing communal activities. There's something deep in human consciousness that responds to the moon. We've written countless poems about it, composed songs, painted pictures. Every culture has moon myths, stories that try to explain its phases, its motion, its influence. The moon as a goddess, the moon as a bowl, the moon as a mirror, the moon as a face watching over us. These myths reflect an intuitive understanding that the moon matters, that it's not just a distant, irrelevant object, but something intimately connected to life on Earth. Modern science has confirmed that intuition, explaining the mechanisms, gravity, tides, orbital dynamics. But the poets and storytellers knew it first. In their own way, there's even evidence suggesting that the moon has influenced human evolution. The predictable tides created by the moon may have encouraged early humans to explore coastal environments, where the retreating tide exposed abundant shellfish and other food sources. Some anthropologists believe that coastal resources were crucial in human brain development, providing the protein and omega-3 fatty acids necessary for larger brains. If this is true, then we owe our intelligence, in part, to the moon, to the tides it creates, to the resources those tides make available. We are lunar creatures, shaped by forces reaching down from the night sky. The ocean itself is teeming with life precisely because of tidal mixing. When tides flow in and out, they stir the water, bringing nutrients up from the depths, carrying oxygen down from the surface. This mixing supports productivity, enabling phytoplankton blooms that feed the entire marine food web. Without tides, the ocean would be less dynamic, less fertile, less alive, and tides create unique habitats. Estuaries, where rivers meet the sea, are governed by the tide, with fresh and salt water mixing in constantly changing proportions. These are some of the most biologically productive environments on Earth, nurseries for countless fish species, feeding grounds for migratory birds, salt marshes, mangrove forests, tidal mudflats. All these ecosystems exist because of the tide. They are shaped by the daily rise and fall of water, adapted to the rhythm of the moon. Remove the tide, and these habitats would vanish. The life they support would vanish with them. So when we ask whether planets affect our oceans, we're really asking whether planets affect life itself. And the answer, at least for the moon, is unambiguously yes. The moon creates the tide, and the tide shapes the living world. Every creature in the intertidal zone, every human who has fished by moonlight, every child who has built a sandcastle just above the high tide line, all of them are connected to the moon's gravity, to the cosmic dance that moves the water. As you rest now, feel that connection. Feel the way your own body echoes the ocean, mostly water, cycling and flowing, responsive to rhythms both internal and external. Your heartbeat is a tide, your breath a wave. You are not separate from the natural world. You are woven into it, part of the vast, interconnected web of life that has emerged on this water-covered planet orbiting a medium-sized star. The moon pulls. The tide rises. Life responds. And you, drifting towards sleep, are part of that response, part of the ancient pattern. But there are still mysteries to explore. Subtler influences, more distant connections. Let's turn our attention now to the possibility that even the most remote planets might whisper their effects across the vast distances of space. The sun is not a steady lamp burning with constant brightness. It's a dynamic star, its surface roiling with magnetic activity, its output varying in complex cycles. The most well-known cycle lasts about 11 years, from solar maximum, when the sun's face is covered with dark sunspots and bright flares, to solar minimum, when it becomes smooth and quiet. Then back to maximum again, during solar maximum. The sun emits more ultraviolet radiation and sends more charged particles streaming into space as the solar wind. This affects Earth's upper atmosphere, causing it to expand slightly. It creates beautiful auroras, the northern and southern lights, as charged particles collide with atmospheric gases. It can even disrupt satellites and electrical grids if solar storms are powerful enough. But does the solar cycle affect the ocean? Does it influence climate in significant ways? The evidence is mixed. Some studies have found correlations between solar activity and climate patterns, but the effects are small and difficult to isolate from all the other factors that influence climate. The sun's total energy output varies by only about 0.1% over the solar cycle, a tiny amount, but potentially enough to nudge climate patterns if the variations persist. More intriguing is the question of what causes the solar cycle itself. The mainstream explanation involves the sun's magnetic field, generated by the motion of electrically conducting plasma inside the sun. The sun rotates faster at its equator than at its poles, which twists and tangles magnetic field lines until they break through the surface as sunspots. Eventually, the field reverses polarity and the cycle begins again. But some researchers have proposed a controversial idea that planetary alignments might influence the solar cycle. Jupiter and Saturn, in particular, orbit the sun with periods of about 12 and 29 years, respectively. And when these two massive planets align on the same side of the sun, which happens roughly every 20 years, their combined gravitational pull is slightly stronger. Could this affect the sun? Could the planet's gravity influence the sun's rotation, or its magnetic field, or the convection currents inside it? Most scientists are skeptical. The gravitational force exerted by the planets on the sun is extraordinarily small compared to the sun's own internal forces. It seems implausible that such tiny perturbations could drive something as massive as the solar cycle. But a small minority of researchers continue to explore the idea. They point out that complex systems can sometimes be sensitive to small influences, especially if those influences are applied at just the right frequency to create resonance. They found correlations between planetary alignments and solar activity that are intriguing, if not conclusive. That if this connection exists, and it remains a big if, it would create a fascinating chain of causality. The planet's gravity affects the sun. The sun's activity affects Earth's climate. Earth's climate affects ocean temperatures and currents. The ocean, in turn, affects weather patterns and the distribution of life. Everything connected. Everything influencing everything else. Yet there's also the question of Earth's orbit itself. We've already discussed how Jupiter and Saturn influence the shape of Earth's orbit over 100,000-year cycles. But there are shorter-term variations, too. Earth's distance from the sun varies slightly from year to year, affected by the gravitational tugs of the other planets as they pass by in their orbits. These variations are tiny. We're talking about changes of a few thousand miles in a distance of 93 million miles. But even tiny changes in distance mean tiny changes in the amount of solar energy reaching Earth. And those changes, accumulated over decades or centuries, might contribute to climate variability. It's like trying to hear a whisper in a noisy room. The signal is there, but it's obscured by louder sounds, volcanic eruptions, changes in ocean circulation, variations in atmospheric greenhouse gases. Teasing out the planetary influence from all these other factors is extraordinarily difficult. Yet the possibility remains tantalizing. The idea that Jupiter, spinning serenely in the outer solar system, might cast a faint influence all the way to Earth's oceans. That Saturn's rings might reflect sunlight that warms water on a distant world. That even Neptune and Uranus, barely visible to the naked eye, might contribute their infinitesimal pull to the cosmic symphony that shapes our planet. It's a reminder that we live in a solar system, not on an isolated world. Every planet is connected to every other by gravity's invisible threads. Every motion matters, every orbit resonates, every alignment creates subtle shifts in the distribution of forces. The ocean feels all of this. Not directly, not obviously, but through the accumulated effects of countless tiny influences over vast stretches of time. The ocean is patient. It integrates signals over years and decades and millennia. It remembers to eye in the sediment layers on the seafloor. Scientists can read the history of Earth's climate going back millions of years. They can see ice ages and warm periods, periods of high sea level and low sea level, times when ocean currents flowed differently than they do today. And when they analyze the timing of these changes, they find the fingerprints of the Milankovitch cycles, Earth's orbital variations caused by planetary influences. The ocean is a library of cosmic history. Every layer of mud, every fossil shell, every chemical signature in ancient ice cores tells a story about how the solar system's architecture has shaped our planet. As you drift deeper into sleep, imagine that story unfolding. Imagine the planets in their stately dance, orbiting for billions of years, their gravity pulling and pushing, nudging Earth's path through space. Imagine the subtle changes accumulating, a slightly different orbit here, a slightly different tilt there, and how those changes alter the climate, shift the ocean currents, transform the world. You are living in one moment of that vast story. One brief chapter in a narrative that began when the solar system formed and will continue long after humanity is gone. But you are part of it. Your existence is shaped by these cosmic forces. Your life made possible by the delicate balance of orbital mechanics and gravitational interactions. And in that cosmic context, there is a strange comfort. You are small, yes, but you are not insignificant. You are part of the pattern. On September 14, 2015, two detectors thousands of miles apart simultaneously measured something remarkable. For a fraction of a second, space itself stretched and squeezed by an amount smaller than the width of a proton. This tiny distortion was caused by two black holes, each about 30 times the mass of the Sun, spiraling into each other 1.3 billion light-years away. The collision released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. And those waves, rippling outward at the speed of light, eventually reached Earth, where human-built instruments detected them. Scientists converted the signal into sound. What they heard was a chirp, a brief, rising tone, like a drop of water falling into a pool. It was the sound of space-time itself vibrating, the universe ringing like a bell. This is what it means to listen to the cosmos. Not with ears, but with instruments sensitive enough to detect signals so faint, so subtle, that they would otherwise be invisible. The ocean does something similar. It listens to the sky. Its surface responds to every breath of wind. Its depths respond to every shift in temperature and salinity. Its tides respond to the gravitational pull of celestial bodies. The ocean is a vast detector, constantly measuring forces that most of us never notice. Scientists have been studying tides for centuries, but they're still finding new complexities. The tides are not simply two bulges moving around the Earth. They're waves that propagate through ocean basins, reflecting off coastlines, interfering with each other, creating patterns so complex that supercomputers are needed to model them accurately. In some places, the tide behaves in strange ways. There are locations with only one high tide per day instead of two. There are places where the tide barely rises at all. There are coastal regions where the timing of high tide changes dramatically over short distances because of the way tidal waves interact with underwater topography. All of this complexity arises from the interaction between simple astronomical forces and the intricate geometry of Earth's ocean basins. The moon pulls, the sun pulls, the planets add their tiny contributions, and the ocean responds, not in a uniform way, but in a richly varied pattern that differs from place to place. Modern technology has given us new ways to listen to the ocean. Satellites measure sea surface height with millimeter precision, allowing scientists to create global maps of tides. Tide gauges around the world record water levels continuously, building databases that span decades. Drifting buoys measure ocean currents, temperature, and salinity in real time. All of this data reveals the ocean as a dynamic, ever-changing system. And woven through all the complexity are the signatures of celestial forces. The twice-daily rise and fall of the tide, the fortnightly spring-neap cycle, the annual variations caused by Earth's elliptical orbit, the long-term changes driven by orbital variations. But there's also mystery. Despite all our instruments and models, the ocean still surprises us. There are currents that appear and disappear. There are waves that seem to come from nowhere. There are biological rhythms that we can measure but not fully explain. Some fish, for example, can detect changes in water pressure associated with tides. They use this ability to time their movements, migrating with the tide to find food or avoid predators. How they sense such tiny pressure changes is still not entirely understood. Some birds can navigate by sensing Earth's magnetic field. How this relates to ocean currents and tides is an active area of research. The ocean and the sky are not separate realms. They're connected in ways we're only beginning to understand. As you rest here, imagine yourself suspended between sea and sky, listening to both. Below you, the ocean murmurs, waves lapping, currents flowing, tides breathing. Above you, the cosmos hums, planets orbiting, stars burning, galaxies spiraling, and you realize they're singing the same song. The rhythm of the waves echoes the rhythm of the heavens. The pulse of the tide mirrors the pulse of planetary motion. There is one music, expressed in different languages. One pattern, appearing at every scale. To truly listen is to recognize this unity. To hear not just the individual notes, but the harmony they create together. To understand that you are not an observer standing apart from nature, but a participant woven into it. Your breath synchronized with the wind. Your heartbeat echoing the tide. Your thoughts rippling like waves across the surface of consciousness. This is not mysticism. This is recognition of connection. This is science revealing what poets have always known, that everything touches everything. That separation is an illusion. That the universe is a single, vast, interconnected system, and you are part of it. As sleep approaches, let that recognition settle into your bones. Let it become not just an idea, but a felt sense. You are not alone. You are held by forces larger than yourself. You are carried by currents that flow through the cosmos. And in that carrying, there is peace.